Okay. Again, thank you for coming and finding your way here, especially compared to the other room. It's much harder to find. I appreciate you coming to my talk. And thanks Professor Zhou for the last introduction. There's only one thing I want to add. I'm also director of a new Industry University Collaborative Research Center for accelerated real-time analysis called CARDA. Yeah, briefly talk about it at the end of my talk. So my talk is about towards intelligent edge. So what does that mean? So we are witnessing an explosion of smart devices on the edge. It is predicted that within 2 years, we're going to have 75 billion of connected devices. And personally, I totally believe in that. But I want to make one correction. So these devices are not just connected, but which is why we used to call them Internet of Things. I think the key difference of these devices, including self-driving cars, and your smart home devices, your Siri, your Alexa, your Google assistants, smart doorbell, your smart cameras. What differentiates them is not the connectivity anymore. What differentiates them is that the processing power, storage capacity, they can be smart. That's why I prefer to call them smart devices. And these smart devices come with a plethora of sensors, and these sensors are generating a lot of data. And it's also predicted that in 2 years, 75% of enterprise data will be processed outside of data center rather than inside of data center. So what does that mean? What does that mean to us? What does it mean to us? Remember that the rate that the devices are growing and the rate that the data they're generating is growing, they're not slowing down. They're in fact accelerating. What that means is that soon, even the cloud will fall short to support the edge devices, the smart devices on the edge, and the data they generate. And how do I know that? We already seen it happen. That's how I know that. Let me give you 2 interesting examples. The first example is a large language model-based chatbots. I hope you all went to Professor Ross' keynote. It's all about LLM. What the LLMs can do and cannot. But LLM is possible because of support from cloud, right? And ChatGPT, of course, is most famous chatbot today. And it gained 1 million users in 5 days, and 100 million users in 2 months. Amazing, right? It is very possible because cloud provides massive amount of resources, right, to train these models with massive number of parameters using massive amount of data. That's why it's possible, right? But even cloud can be not scalable enough. Just over 1 week ago, immediately after OpenAI released their latest, most powerful GPT model, it's called GPT-4 Turbo. Another user of ChatGPT saw this error message. It is saying that ChatGPT is over capacity. And some other own explanation is, sorry, our system is overloaded. A good example of this, that cloud is not able to keep up with the demand coming from the edge for LLM-based chatbot. Let me give you one more example, which is also very interesting. Self-driving cars. And all of us probably have seen those self-driving Waymo cars strolling around Tempe, AC campus, right? And they are made possible also because of cloud. Each self-driving car is estimated to generate 7 terabytes of data, per hour. Only cloud has the capacity to store and process all that data. But even cloud can be not reliable enough. So on that top picture you saw there, those are the, let me go back. Those are the Cruise self-driving cars. They have a committed to run in San Francisco. And ironically, those cars, they will not drive it was stuck at San Francisco downtown. And they caused a traffic jam. Why? Because there was a music festival nearby. The caused a wireless connectivity issue to all the cars. And when a self-driving car goes this internet connectivity, what does it do? Stop. It cannot drive anymore. Right? And so I did not witness that. I was not at San Francisco at the time. But over a month ago, I was running around SDFC, ASU's sports complex. I saw this a bunch of adorable self-driving food delivery robots. They were stuck at an intersection right outside the SDFC. What were they doing? Maybe they were taking a break. But guess what? Last Saturday when I was running again, I saw a Waymo car that was stuck at the exact same intersection. And they blocked a long queue of human driving cars. Of course, they were all honking the horns. Okay? And only after 5-10 minutes later, the car started moving again. Probably a remote, because a remote operator came to rescue. So my guess is that that particular intersection is a wireless diode and causing trouble to whatever that is self-driving. So now we know the cloud will soon become insufficient to support the edge, the rapidly growing edge. What do? The only way forward, the only solution is to make the edge intelligent. And don't forget, I mentioned that upfront that the edge is smart, right? So all of these devices, they have processing power, they have storage capacity. And we can also deploy edge servers and even edge data centers between smart devices and the cloud, right? At the ISP data centers, your CDN data centers. So together, we have the potential to do computing on the edge. That's why I call edge the new frontier of computing. And if we can make the edge indeed intelligent by making the smart devices indeed smart, then we can reduce the data transfer, storage, and processing need in the cloud, therefore improve scalability. And then we can also make decisions in a more responsive way, because by making decisions, by deriving intelligence and making decisions right there on the edge, we can achieve real time, and we are not affected by whatever is happening in the cloud or over the network between the edge and the cloud. And moreover, we can also utilize the knowledge about the tasks on the edge, the data on the edge, to customize machine learning models. And we can also improve privacy by learning on the data on the edge without having to share the data with anybody else, including the cloud. Let me give you two examples how we can make edge intelligent. And both of them are coming from my students' research. The first one, what we are trying to do is to use LiDAR cameras for crowd management. And we have this wonderful, so in collaboration with the University Technology Office, we have deployed smart blue light poles at several different locations on campus. This is one of them installing in front of MU, that's basically the student center. If you notice, I'm not sure you can see the data here. On top of this pole, we have LiDAR cameras. Okay, we have several LiDAR cameras facing different directions where people may be passing by. And what we want to do is use the LiDAR, the images collected by the LiDAR to count the number of people passing by, and use that to estimate the amount of traffic for crowd management. And not only this smart black pole has sensors, right, like LiDAR cameras. Inside, it has computing devices that can be used for edge computing. Indeed, we implemented the machine learning model, and we can write on the embedded device, which is installed as part of inside of this pole, and we can use it to count people who are passing by. And this GIF illustrates the 3D cloud that's come from the camera, and the clusters indicate different objects that are recognized from the LiDAR images, and the labels indicate the classification results, okay, whether those clusters are human or not. And we are able to do this with good accuracy at the same time, achieve low latency, because this is done right there on the pole, rather than in the cloud. And we can also achieve strong privacy because the data does not have to leave the pole. Let me give you another example. This is related to self-driving cars. So one of the important tasks of self-driving cars is stay in the lane. And here is another view that shows how we can use edge-enabled model training to achieve this lane centering. Okay, more specifically is the steering. If you can see the steering angle here, steering angle prediction. And the right line indicates the ground truth basically is the correct steering angle, given the current the location of the vehicle on the road. And the blue line is the prediction result. So you can see the prediction accuracy is pretty good because the blue line closely follow the right line. And we are able to do this by training the model entirely on the vehicles instead of using the cloud. And by doing that, we can achieve high scalability because we're not relying on the cloud to train the model. And we can also achieve strong privacy because again, the training data that each vehicle is providing does not have to leave the vehicles. And this again is our own research. So I'll give you two success examples, sort of success examples of achieving edge intelligence. But overall, this problem of making edge intelligent is not easy. There are many challenges. We have to recognize that compared to the cloud, edge resources, they have much limited capabilities and capacities. And those resources, unlike cloud, which is more homogeneous in terms of the hardware and software, the resources we have on the edge are highly diverse, and they are also highly distributed. So our research, a lot of our research efforts are focused on addressing those challenges. And for instance, how do we create accurate edge models? How do we effectively learn our edge data? How do we utilize distributed heterogeneous resources? And how do we support diverse applications on the edge? Given the limited time, I'll focus on only the first two questions today. Spend more time probably on the first one and do as much as I can on the second one. So the question is, how do we create accurate edge models given the resource constraints of the resource of the devices? They have limited memory, limited processing power, but we still want to achieve good accuracy and good speed. And our solution is based on model compression. Model compression basically means that we start with a large state-of-the-art model, probably trained in the cloud, and we try to compress it so that we can deploy it on edge resources, right? So let me give you some quick background, okay? So you can understand what we are doing. There are two main approaches for compression. One is quantization, which basically means that convert the floating point numbers in the model to low precision numbers, 8 bits, 4 bits, even 2 bits. But the quantization often leads to large accuracy loss. And the other way is model pruning, which means that we find out which parameters in the model are not important, and we remove them. Second approach tends to give a better result in terms of accuracy. So we focus on model pruning. I need to go a little bit faster. Now, when it comes to model pruning, there are also two different approaches. So this illustrates a typical convolutional layer, and all the things here, they are basically groups of weight parameters that are called filters. And basically, what we're trying to do is that we want to remove the filters, okay, or the parameters of the filters, okay. So then we have one approach called unstructured pruning. It removes individual elements of the filters, right? And this approach leads to better accuracy, but it's very hard to accelerate on GPUs because the filters become irregularly shaped. And structured pruning would remove the filters entirely, so that the end result, this prune model can still be easily accelerated. Therefore, we go with structured pruning. And one more thing I want to tell you in the background is that when we do pruning, typically what we do is that we train the model, okay, until it fully converges, then we prune, and then we retrain the prune model. Okay. Can do it only one time, it's called one-shot pruning, but it's very difficult to recover the accuracy loss if we do it one time, or we can do it repeatedly, and that's called iterative pruning. And so we focus on iterative pruning. And putting everything together, finally, one more thing, okay, is another pruning method today. They require human expert to decide the pruning parameters, like how many parameters to prune for each layer, and what is threshold used to decide which parameters should be pruned, which should be kept. Right? So we want to advocate automatic pruning so that the pruning method can actually be usable. User just need to give us what you want. What is your accuracy target? What is the model size target? What is the complexity target? We automatically give you the model that meets your target. So putting everything together, our goal is automatic pruning for creating small, accurate, and hardware efficient models. Our solution is adaptive, attention-based, iterative, structured pruning. Okay. By being adaptive, we can make it automatic, and we propose a novel attention-based method to identify insignificant parameters to prune, and by using iterative pruning and structured pruning, we are able to generate accurate models, more and accurate models that at the same time are also hardware efficient. Okay. Moving on quickly, so this is the overall. The first step is that we designed a iterative structured pruning method. I just quickly go over this, but the basic idea is based on this lottery ticket hypothesis, but no one had been able to make it work well for structured pruning. It was originally proposed for unstructured pruning, and we were the first one to do it. And the second aspect is we propose now a new method to identify, to differentiate significant parameters from insignificant one, right? Because we want to remove only the insignificant one, we want to keep the significant one, right? And this method is based on attention. The basic idea is that we look at the activation value of a filter, and these pictures illustrate the 2D activation maps coming out of the model. And if you can, for different filters, okay, you can see some of the filters like 2, 14, they do not capture anything. And those are the filters, if we can see them that they do not capture anything, then we can also mathematically find a way to remove them, right? And that way is this attention function. So we designed the attention function to map this 2D activation feature to a single 1D value, and then we can use that value to prune filters. Okay? If we set a threshold, and if this value, the value of the attention function is below the threshold, we remove that filter. And finally, we want to make, like I mentioned earlier too, we want to make the whole pruning process automatic, right? So so our pruning is policy based. User just tell us what you want, right? And for instance, the user's policy might be, I want to guarantee certain accuracy loss, maybe 1% accuracy loss. Okay, you have a given model that guarantees that, and at the same time, let's try to minimize the model size. And the way we do is that we automatically adapt the parameters that we have to use. Like instead of, in contrast to existing methods, we have to manually tune those parameters. We automatically adapt these parameters, and according to the target, the pruning target, right? So this pipeline shows how everything put together in our approach. So we have attention-based method to identify insignificant parameters, right? And at the end, we adapt threshold automatically depending on how far we are from the target. If we are far away from the target, we prune more aggressively. If you are getting closer to a target, then we prune more conservatively. And if we miss the target, we have to roll back and do it again. So the whole process is automated. So let me quickly show you some results. So we did a lot of experiments, some state-of-art image classification models, and we can see different policies based on accuracy loss, model size, and the speed. So let me just explain why. Okay, because I'm running out of time. This table shows the result from this policy is to minimize model size while given accuracy target. And the target here is 0% loss, 0% accuracy loss. It means that the probe model should have the same accuracy as the original model, right? So the last two rows are our results. The others are from the related work. Right? So if the policy is to minimize, is to guarantee the accuracy loss, basically low accuracy loss, and minimize the model, we have the smallest model because we achieve the highest model size reduction. If the policy is to guarantee the accuracy loss, okay, and minimize complexity, so FLOPS is a metric for measuring complexity. We also have the noise complexity because we achieve the highest FLOPS reduction. So, and this result is for different accuracy targets, and just give it. And this table is for different policies to minimize accuracy loss, give a FLOP reduction targets. This means that I want to guarantee the speed, but I want to minimize accuracy loss. So I may also skip that. And the more results for another state-of-the-art model on a much bigger data size, skip that too. Okay, so I'm done with my first part, the first part of my talk, right? The question we are trying to answer is how to create accurate edge models, and our solution is adaptive activation-based iterative structure pruning. And the second part of my talk, I'll try to as much as I can, is how to effectively learn our edge data. We have privacy concerns. The users do not want to share their data with other people, not even the cloud, and the models are heterogeneous, and the distribution is wide. So, and just quickly go over it. So our solution is based on bidirectional learning, and this shows the typical approach to bidirectional learning. So every model, every device here is treated as a vehicle trained model data to model locally using local data. Okay, so they don't have to share them with anybody. Everybody upload the local model to the cloud. The cloud averages the local models, and then other devices will download the aggregated model and do that repeatedly until the model converges, and then finally, the final model can be deployed. So there are multiple limitations of this typical approach to bidirectional learning. One, it does not support heterogeneity because all the models on the devices and in the cloud, they all have to be the same, which automatically means that we cannot use large models because the devices cannot train large models. Okay, and also it does not address data heterogeneity well. And there's a lot of overhead involved because all the models have to be sent to the cloud, and it has to be done repeatedly. And finally, even to the privacy, this approach is not strong enough. Even though the devices don't have to share data with the cloud, they still have to share their parameters, and there are ways to steal information from the weights. Okay, so let me jump ahead. So our solution is to use knowledge destination, okay, for further learning. And the idea is that we treat the devices as teachers and treat the cloud as a student. And we ask the teachers to help train the student. So in order to do that, the teachers which are allowed the devices, they do not have to share their weights with the cloud. They only need to share their output with the cloud. And then using knowledge distillation, we are able to train the student. And this solves the limitations of the typical federated learning approach, because now the way that works like is again, the device will train the model locally, and they only upload the output to the cloud. And then the cloud will use destination to generate the global model, and this only to be done once. But in that way, no communication overhead, because instead of sending all the weights, we are sending only the outputs, which is much smaller, stronger privacy protection because weights are also not shared. And low computation overhead with whole thing is one shot. And finally, you might ask, how do we deploy the final model, which is now large model? Okay, we do Pronit. I already covered that in the first part of our talk. Okay, so I entirely skip this part, the station, just quickly show some results. Let me just show you this result. So these two figures compare our approach, okay, the proposed one with the existing Python learning, Python destination methods. And let's just look at diagram on the right. So the y-axis shows the loss value, so the lower the byte and the green line clearly is the lowest one, and also it converts much faster in fact the state of algorithm works. Okay, so let me conclude. And so we covered two problems today. The first one is how do we create accurate edge model? Second, how do we effectively learn our edge data? Right. For the second problem, our solution is federated differentiated distillation. And we also have done work to solve other problems like how do we utilize distributed heterogeneous resources. Our solution is function-based edge computing. And how do we support diverse edge applications? And we are working with domain experts to develop solutions for things like stress management, things like the traffic light management. So acknowledgement are really important. Sponsors. I do want to thank my students, my wonderful hardworking students. Of course, everything I'm presenting today are their hardworking results. Obviously, they're not working here, but in the pictures, but they do work hard. Yes, and I do want to spend just 10 seconds to introduce this center to everyone. So we have this new center. With the sole purpose of the center is for facilitate industry, university, and government partnerships. And we have 3 partner sites in 3 other universities. So industry member become a member, the industry company become a member of the center can gain access to faculty and students of all the 4 universities and to be able to select projects that benefit the company the most from all 4 sites. If you are interested, you visit our website or you email to that address and they reach me directly.